Okay, yeah, thank you for handing over the word. So I'm Dennis. I'm a researcher at the Delft University of Technology. I'm working in the Micro-Aerial Vehicle Lab. I will explain what it is on the next slide. And today I will give you a brief introduction to the tactical detect and avoid within a horizontally constricted airspace during this presentation. So first, what I already told, I'm part of the MAVLab. So we focus on autonomous flight of small to tiny vehicles. And our vision is if we make algorithms work on a small drone with a small computer chip, it will also work on a big drone, as the computational power of those big drones is way bigger than the small drones. So this presentation will mainly focus on the detect and avoid. We started with detect and avoid in the Futura project. It was a project above the campus of Delft, and we successfully avoided each other. So we flew 2 drones and we showed some avoidance maneuver there. Now we further developed the algorithm to also use in the SAFIR-Med project. We are also participating in the Metropolis 2 project. There's also a project going on at this moment, and the demonstration will be, I think, in September for that at Valkenburg in the Netherlands. And we are also one of the drone operators or manufacturers here in the SAFIR-Med project, as you can also see on the slide. So before telling you how to avoid a conflict, I will first define what a conflict actually is. Today I will focus on a horizontal conflict resolution method. So that means that we don't change our altitude to avoid the conflict, but we'll only change our speed or our heading, or both of them. So actually a conflict can be seen as like an area around a drone that needs to stay free of other traffic, the protected zone. At some moment we can encounter an intruder, and if we expect that this intruder will fly in our protected zone in the future, as you can see in this picture, we have to make sure to avoid it. So if we expect an intruder in our protected zone in the future, there is a conflict we have to resolve. So for the SAFIR-Med, we are focusing on a tactical detect and avoid. This means if the strategic detect and avoid is not working, then we can still in-air avoid other traffic. So this is based on a small time scale of about 30 seconds before the conflict actually happens. It can be run fully autonomous, and because of using USpace, we can basically use that as our sensors. So we don't need equipment on the drone, we only need a data stream of traffic, positions, and speeds from a USpace service provider. So how do we resolve our conflicts? We make use of velocity obstacles. I will now introduce you to a velocity obstacle. Here you see the ownership, that's the drone we are controlling, and there is an intruder in the airspace with a protected zone around it. So we can draw a triangle from this protected zone of the drone to our own drone, and we can look at our relative velocity to this drone. And if this relative velocity is pointing into this conflict cone, as depicted here on the slide, we have a conflict we have to resolve. Now we have to select a new direction and a new speed to resolve this conflict. So what we do, we translate the conflict cone with the intruder speed, such that we have an absolute speed reference frame again, and we see that our own speed is now pointing in this red area, and we have to change our own speed of our own drone. We can do that by changing heading, changing speed, of doing both of them to get out of this velocity obstacle. So how this works, we have our own drone with a certain speed directed in the north in this case. We add all velocity obstacles together from the drones that are flying in our airspace. We have to add the limits of the drone. We have a minimum and a maximum speed. So actually, you see a donut here, and all speeds depicted by the donut we can choose to perform an avoidance maneuver. So the green area is conflict-free. The red area we have to avoid, because then we will conflict with other traffic. So our algorithm can calculate the conflict resolution in several manners. We can just change the speed factor in the optimal way, so the smallest change. We can say, okay, we only change direction, so with heading. Or, for example, if we have a target point, we can also try to perform our avoidance maneuver towards the target already, that we're already directed in the right direction. So what we had to add for drones in a conflict resolution method, and that's never referenced in literature before, is that we have an assigned area which we cannot escape during our operation, so the geozone. So actually, if we have a conflict in this geozone, I think the other drone disappeared here, but if we have a conflict here, we have to resolve it in this geozone. And on the solution space diagram at the right side of the screen, you see some elliptical shape. And this is basically the inclusion of this geozone in the algorithm. So basically, our algorithm fulfills two requirements. We will resolve the conflict, and we will also stay within our predefined geozone, such that we cannot fly towards airports or whatever. So we also performed simulations already on this topic. Hopefully the video will work. So on this simulation you see two drones on the map. At the left side you have UAV1, at the right side you have UAV2, and you see they are flying in some corridor, surrounded by blue. UAV1 has priority, so UAV2 needs to avoid UAV1. You also have the two solution space diagram at the right. The upper solution space diagram corresponds to UAV1, the one with priority that is shown at the left of the map. And the lower solution space diagram belongs to UAV2 that will perform the avoidance maneuver. There is also a black line drawn in the solution space diagram, and that is the speed factor of this drone. And you will see that at the end, when we perform the avoidance maneuver, that this black line is not pointing in a red zone anymore, but in the gray zone, what is safe to avoid. So hopefully run the simulation now. Yeah. So now the drones are in conflict, and in a few seconds we'll see that drone 2 will try to avoid drone 1. We'll also see, yeah, there you saw it. So it's now flying away from the UAV1. We see the black lines, so the speed factors of both drones in the solution space diagram now pointed in the gray area, so the resolution free area. And we can see that the drones reach some point where the conflict is resolved, and then they will head back to their target again. So in the SAFIR-Med project, we generate a waypoint that we add to our flight plan to perform this avoidance maneuver. I think it will soon go back to its original route. Yeah, here we see it's resolved, and now it goes back to its original target again. So with a small deviation of flight path, we can already resolve conflicts here. So yeah, I would ask if you're interested and want to know more about those algorithms. I will be standing down this afternoon, and you can ask questions at our booth. Okay, thank you for your attention.